Our next speaker is Véronique Bazier-Matte from Université Laval. She will be talking about non-orientable surfaces and representation theory. And yes, well, go ahead.
Well, thanks for the introduction and thanks for the invitation to speak here. I'm really excited to show you my work about the connection between non-orientable surfaces and representation theory that I've done with Aaron Chan and Kayla Wright. So what I'll do today, I'll first give you a short overview about non-orientable surfaces. Then I will briefly explain what has been done between, well, for the connection between non-orientable surfaces and representation theory. And finally, in the last part, I will show you the content of my paper, where we try to adapt what was known for the connection between orientable surfaces and representation theory, but to the non-orientable case. So first, let's start with a bit of background for non-orientable surfaces. So up to homeomorphism, a non-orientable surface is determined by three things. So first, its number of boundary components. Second, its number of mark points on each boundary component. And lastly, the number of cross-cap, which is an analysis where antipodal points are identified. It's kind of a non-orientable version of a genus. Let's look at an example. Here I have, well, let me change that. So I have a surface here with one boundary component, two mark point, and one cross-cap here in the middle. If I do a few steps, I can see that this surface is indeed a Mobius strip. It is maybe a bit more familiar like this. And in 2015, Dupont and Palesi defined quasi-cluster algebras that are a generalization of cluster algebras, but arising from non-orientable surfaces or orientable surfaces. So the idea is to triangulate a surface, orientable or not, with arcs, and we'll have two kinds of arcs. We'll have regular arcs as we know them from the orientable case, it's just arcs between mark points, and we'll have what we call quasi-arc that are one-sided closed curves. So a closed curve is said to be one-sided if you can take a normal vector to the surface at one point on the curve, and you follow the curve and go back at your point with the opposite normal vector. Let's look at an example. Here is a quasi-arc. So it is a one-sided closed curve on a Mobius strip. If I take a cover of the Mobius strip, it will be that loop here that goes all around, or maybe it's more familiar like that. It will be a loop going all around the middle of the Mobius strip. Here is another example of triangulation. It is not obvious like that it is a triangulation of the Mobius strip, but if I draw it on the cover, I do see actually triangles. So it makes sense to call that a triangle. So that's it for the brief introduction about a non-orientable surface. Let's step aside from that for now and talk about what we know about representation theory for orientable surfaces. So we know that we can associate a quiver QT with a potential WT to a triangulation T by first fixing an orientation for T. So of course, if we start from a non-orientable surface, all of that fails. And we'll have KQT to be the Bath algebra of the quiver QT, IT to be an ideal coming from this cyclic derivative of the potential. And by quotienting the path algebra with the ideal, we'll get the Jacobian algebra. If I draw quickly an example, I have a triangulation here. I fix an orientation for my surface. It will give me this quiver. I take the potential given by the internal triangles. The potential will give me an ideal, and I will get a Jacobian algebra. We also know by Assemblus, Charbonneau-Jourdain, and Plamondon that GT is a finite dimensional gentle algebra. So we know stuff about what happens when we start from an orientable surface. We also have a lot of nice correspondences between what happens on the topological sides and on the categorical sides when we start from orientable surface. And I don't want to go through all these correspondences. I just want to emphasize that there are a lot of known stuff, and our goal was to try to adapt all that to the non-orientable case to see if we could still have these nice correspondences and how does it work. So we don't know anything about how to do representation theory from a non-orientable surface. Well, we we don't know a lot, but we do know that every non-orientable surface admits an orientable double cover. So it means that we can translate everything that is non-orientable into an orientable surface. Furthermore, if we start from a triangulation without quasi-arc, it can be left to a triangulation of a non-orientable surface. Here is an example. I have a triangulation of a non-orientable surface. It does not contain a quasi-arc. If I take the orientable double cover, I will obtain that triangulation. It is a standard, a usual triangulation of an orientable surface, so we know how to deal with that. However, if I take instead that triangulation, it is a triangulation of the Möbius tube as well, but it contains the quasi-arc. And now if I take a double cover, the arc A is sent on 1 and 3, 2 regular arcs, but the quasi-arc C is sent on the loop 5. So it is not a triangulation, and we know less about that. So one corollary that we get is that if we start with a triangulation without quasi-arc, we'll give rise to a quiver QT, Q tilde, and a potential W tilde, such that J tilde is gentle. Here T is a triangulation from a non-orientable surface, and T tilde is in the orientable double cover. We can also get a cluster category T tilde, but we have to start from a triangulation without a quasi-arc. So the question is, what can we say about the topology of the non-orientable surface and the cluster category C tilde? So even though that we choose to start from a triangulation without a quasi-arc, is there anything that we can say about all the non-orientable surface, even the quasi-arcs? And because we take the double cover, we'll have a kind of involution anti-symmetry that will appear everywhere. So in particular, we'll have that Q tilde, W tilde is anti-symmetric. It means that it admits a fixed point free anti-automorphism sigma. So sigma applied to an arrow alpha from I to J will give an arrow sigma alpha from sigma J to sigma I. Sigma applied to the potential is a potential, and sigma applied twice is the identity. If I look at an example, I start from that triangulation here of a non-orientable surface. It does not contain a quasi-arc, so it's fine. I plane it in an orientable double cover. It is a triangulation as we know them. I can get a quiver out of that, a potential. It's the same as I've shown you before. And I have my anti-automorphism sigma that sends 1 on 3, 2 on 4, and any arrow alpha I on beta I. If I apply sigma to W, I will also get back to W. So sigma acts only on the quiver, but we'll have the same kind of behavior of this anti-symmetric thing on the module category. So sigma induces a contravariant functor nabla on the module category that will send a vector space Mi on the vector space M sigma I and a map M alpha on the map negative M sigma alpha. Let's look at an example. So I take the same quiver. I want to look at the module 1 to 4. 1 to 4 is given by the arrow alpha 1, alpha 2. So if I take sigma applied to alpha 1, alpha 2, I will get a beta 1, beta 2. I have to reverse the order. So it will give me 2, 4, 3, and by beta 2, beta 1. So that's how we can see this involution. Now we have to be a bit careful about what does it mean to be indecomposable in this setting, because we have seen in that example that since I take a double cover, one arc on the non-orientable triangulation can give 2 arcs in the orientable double cover, but it is not always the case. If I take a quasi-arc, I will only get 1 loop on the orientable double cover. So we have to be careful about how we define to be indecomposable. So here is a definition proposition. We'll say that a J tilde module is epsilon indecomposable if one of the following holds. So either M is one-sided, so just mean that M is indecomposable as a GT module, or M is decomposable, M is L plus nabla L. So it is decomposable, but in a very specific way. It can be written as L plus nabla L. And if ever L is not isomorphic to nabla L, we'll say that M is split. Let's look at an example. So it's the same setting as before. I take the following representation. of course, it's indecomposable, so it will set to be one-sided. If I take this representation instead, it is decomposable, but I can see that N2, this representation here, is indeed nabla N1. So it means that N is split and is said to be epsilon indecomposable.
Let me just tell you have about a minute left.
Oh, okay, great, thank you. So we can make the jump from the module category to the cluster category and keep this notion of one-sided module and split module for objects in the cluster category. And we have the following theorem. So we have a bijection between irregular arcs on the non-orientable triangulation and the split objects in the cluster category, and a bijection between the quasi-arcs and the one-sided objects. So it will just finish with that example. I have the quasi-arc here. It gives me that loop in the orientable double cover that is associated with that one-sided epsilon indecomposable object. And on the other side, I have that arc here that is associated with these two arcs that give me that object in the cluster category that is split. And yeah, that's it. I will skip that then. Thank you very much.